What is spin? It's something that apparently some particles have that you can measure, but what is it? In this video, I'll explain how we know spin exists, but also why we don't understand it. Spin was a latecomer to the quantum mechanics party. Even after Schrödinger wrote his famous equation and everything seemed to be working, people didn't realize it existed. Then people realized that some particles seemed to have odd magnetic properties the original quantum mechanics didn't predict, and the source of that was labeled spin. To understand this, we're going to need one piece of classical electromagnetism theory. Whenever a charged particle moves, it creates a magnetic field. This is pretty amazing, and you can see it for yourself by putting a compass next to a charge-carrying wire. In fact, if you have a charged particle going in a small loop, this not only creates a magnetic field, that field pretty much looks like it's from a bar magnet. So then we expect charged particles moving around in circles to act as little magnets. Since that's something we know from classical physics, it was built into quantum mechanics too from the start. But eventually some experiments showed that there must be some other source of magnetism. I'm going to explain one of those, a simplified version of the Stern-Gerlach experiment. Let's say we have a bunch of electrons by themselves. They are charged, but they're not doing little loops, so they shouldn't be magnets. We test this out by putting them in a Stern-Gerlach apparatus. I'm not going to explain how the machine works, but what it does is this. If a small magnet is placed inside, it measures its orientation. If the magnet's north pole is up, it exerts an upward force on the magnet. If the magnet is the other way around, it exerts a downward force. Of course, there are other orientations. If the magnet is like this, the magnet is still somewhat pointing up, so the force is still up, but smaller. It's proportional to how much this magnet is pointing in the up direction. Similarly for this magnet pointing down. Say a magnet is on its side, then it has no force at all. But these aren't the only ways the magnet can be oriented either. It could be forward or backward or left or right or any combination. And so what happens there? Well, this machine only measures how much the magnet is up or down. If the magnet is like this, it's still pointing a bit upward. On the other hand, if the magnet was just pointing left or right or forward or backward, it wouldn't feel any force, and so it would go straight. So what we expect is, if we shot through a bunch of magnets in random orientations, they all land between here and here, and in a pretty smooth distribution. Of course, if we threw in a non-magnet, it wouldn't feel anything and just go through. So that's what we should expect with electrons. But we do the experiment and find something really odd. The electrons do experience forces as if they're magnets, but they don't spread out smoothly either. Half of them go up to the same height, and the other half go down, again to the same height. Let's look at this second mystery first. If electrons really are magnets, we expect them to be randomly oriented, but these results would be like saying that, for some reason, half of them were pointing exactly up, and the other half exactly down. Well, maybe we did something very wrong when we prepared them that meant this happened. So, to test that, let's do something clever. Let's turn the Stern-Gerlach machine on its side. What that does is, now the machine is measuring how much a magnet is pointing to the left or right instead of up or down. The more the magnet is pointing to the left, the more left it goes. If a magnet isn't pointing either left or right, it just goes through. Now let's use the same source of electrons we had before. We think that they're all pointing up or down, and so they should just go through this machine and they shouldn't be deflected at all. What happens? Half of them go right and half of them go left. So then they were actually oriented left and right all along, but that can't be right either. Let me explain how to think of this in the framework we built up in the last couple of videos. I can measure the up or downness of a particle, so that is an observable. What are its eigenstates? Well, this experiment showed that the particle can only be fully up or fully down and nothing in between. So they are the only two eigenstates. We'll call them spin up and spin down. Now we can apply the quantum mechanical principle that to fully describe the wave function of this particle, we only need to describe it in one basis. So I can fully write the state of this particle in terms of up and down. This is weird because in classical physics, it wouldn't be enough to tell you the state of the magnet. I can't just tell you how much it's pointing up or down. I need to also tell you how left or right it is and how forward or backward. But in quantum mechanics, this is enough. Let's see what happens when we do some arbitrary combination. Here, since the square of this number is bigger, it has a bigger chance of being spin down, but it can still be spin up. It doesn't go 3/4 of the way down ever though, it's only ever up or down. But what about if I flip the machine on its side to measure the left-rightness? In quantum mechanics, if you tell me the wave function in terms of up and down, I should be able to figure out what the wave function is in terms of left and right. To be able to do that, we just need to know how to convert up and down to left and right. But how? The coefficients should be equal in size if we use this classical analogy. A particle that's fully up can't be pointing either left or right at all. A quantum particle that's up but is being measured for left or rightness must go one way or the other, but at least it shouldn't be biased towards one side. Now we need to decide the sign of each of these. If we agree to call this right and that left, then it turns out that the right way to do it is this. And this is something you'll recognize from the last two videos. Okay, so now I've shown you how quantum mechanics deals with spin, let's return to the much more difficult question. What is spin? The electrons aren't doing little loops, so why are they magnetic? This was what was originally proposed. The electrons are spinning on their own axis. The idea is, if you have a charged ball that's spinning, that means bits of charge are moving in a circle, and so it creates a magnetic field like a bar magnet. But we know this is wrong. If this was really true, we can calculate how large the electron should be. It's bigger than the whole atom. It also makes some other incorrect conclusions. These days we think the electron isn't a ball, it's an infinitely small point, and that can't spin. I think this image of an electron spinning is really more harmful than helpful. Not just because it makes all kinds of incorrect predictions, but because feeling like we understand something stops us from asking what it is. But making this video, I realized that there are lots of other physics terms that I don't understand. What is energy? What's charge? It seems like we define these things by how we measure them, and then the same is true for spin. Spin is the thing that makes particles act a bit like magnets. I really hope that in the future, as we understand more physics, more of these terms can be understood in terms of deeper physics. At least there's some hope for spin. I told you that spin had to be added into quantum mechanics in an ad hoc way. This is true, but when Dirac tried to merge standard quantum mechanics and relativity, something in his new equation acted a lot like spin. While this was awesome, I don't feel like it solves the mystery of spin, because while it comes out in the maths, it still doesn't explain what it is or why relativity demands it exists. But maybe there are some properties of physics that we can never understand, and maybe spin is one of them. There was so much more I could have said about spin, but I ran way over time. So I thought it would be fun if you guys taught each other instead. In the description, I put a whole lot of questions I didn't answer in this video. I would love if you picked one or more of these or found your own and did some research. You can present your work in any format you want, as a YouTube comment, on any of these social media accounts, or on your own website, etc. And it would be kind of amazing if you want to make it into a video, but I know that's a bit daunting.